All right, adding and subtracting fractions. Not a big deal, just kidding, it's huge. So let's go ahead and talk about common denominators. This is where the whole thing, adding and subtracting fractions is all based around the common denominator. So just so we're clear, the numerator is up top, denominator is down on bottom. And then we can do this as north and down if you have problems remembering where a numerator denominator is. North is up, denominator down. So if you have a fraction, say for example 1/4, and then you have another fraction, 1/4, these have common denominators. This is what is required so you can compare the appropriately sized parts. Because let's say we had a half. Well, a half looks like this. Okay? And here's what a fourth looks like. So whenever we're going to put 1/4 with 1/4, it's pretty easy because you just go, I'm just going to add another fourth to that. Cool, I have 2/4, which equals 1/2. Whoa, hold on. So this is why we're talking about equivalent fractions and common denominators, because this type of thing is what makes fractions confusing. So whenever you have a half and you want to make an equivalent fraction with a common denominator, you can see here that we have a 4 up here. How are we going to turn this into a 4? All right, well, we can double the amount of parts we have, and it looks like this. Now there's 4 parts, and you can see that that's equivalent to 2/4. So if I had 2/4 and I added 1/4 to it, you can see I have 3/4. So creating equivalent fractions is why common denominators are important. Without common denominators, you're going to struggle to create equivalent fractions. Equivalent fractions need to be created with common denominators to be able to add fractions up. Now, whenever we're talking about using the multiplication chart, if you wanted to say 42/63, and you're sitting there going like, man, that sounds really tough to add or subtract. Well, just follow it over to the left. I found 42/63, and that's 6/9. You're sitting there going, well, 6/9, hold on. I know that something goes into that. See if you can find 6/9. So here's 6/9. Goes down to 2/3. So we just simplified a fraction using no math. We found it on the multiplication chart, and we simplified a fraction all the way down to 2/3. This is just an easy way to find equivalent fractions. For example, if you had 2/3, then let me clear this off. If you had 2/3 and you wanted to add, add it to 5/6, well, then you know that, okay, so 2/3 and 5/6, those do not have common denominators. So I can't add or subtract them. So what I can do is I can follow 2/3 until my denominator is 6. Oh, hey-oh, there we go. Okay, so my equivalent fraction would be 4/6. This would make a new problem for me. If I were adding 2/3 and 5/6, I could say 4/6 plus 5/6. Add the numerators, done and done. So every problem that we're going to go through, I'm going to highlight everything that needs to be done on the multiplication chart, and we're going to go through a addition problem and a subtraction problem. The process is going to be replicated exactly the same over and over and over and over. It will never change. So let's go with something crazy. 7/8 plus 1/3. All right. So we can see here that the denominators are not the same, 8 and 3. We know that 8 and 3 are not the same. Here is one way you could do this. And the quicker way, the quicker version of this is using the multiplication chart, but I want to show you that if you don't have one, this is one way you could do it as well. So 8 and 3. Just count by 8s. 8, 16, 24. All right, whenever we are starting to count by the big number, you know you're going to count by the smaller number more. So let's not count as many for the big number and count more for the small number. 3, 6, 9. I put 19. Okay. Wow. 9, 12, 15, 18, 21, 24. All right, so what we're looking for is the lowest or the smallest number that matches up. So far, I didn't see an 8 anywhere in the list of 3, so that's no go. We saw 15. That's really close to 16, but no go. We can see that the only one that we found that they had in common were 24. All right, I'm going to go back to the multiplication chart and replicate this process. So 8 and 3, all right? So I can count by 8s, all right? And then count by 3s, and you can see the process is exactly the same. All I have to do is look across the row and find out which number matches up first. It was at 24 again. There are going to be other numbers that match up that are greater than 24, but you want to have the least common. That way you have less problems reducing at the end of the math problem. Because whenever you start adding this stuff up, you could potentially have to come back to the multiplication chart and simplify. So how does this process work? All right. Well, you've got 8, and what did you multiply 8 by, or how many 8s did you count to get to 24? 1, 2, 3. So that's what I'm going to be multiplying my 8 by. I'm going to be multiplying it by 3. So with creating equivalent fractions, whatever you do to the bottom, you have to do to the top. So I'm going to do the same exact thing. And this is where we were struggling whenever we were going through it, practicing together, is rewriting this stuff in a neat, organized manner so you understand what you're doing. Let's count how many 3s we had to count. 1, 2, 3, 4, 5, 6, 7, 8. All right, so we know that we have to multiply this by 8. And whatever we do to the bottom, we do to the top. So this creates some math problems for you to do. And this can go directly back to the multiplication chart. No reason to think too hard. All right, so I know I have a problem right here. It says 7 times 3. 7 times 3. Let's go back. I have no idea. 7 times 3, 21. Cool. Okay, so 7 times 3 is going to be, I'm just going to rewrite this down over here. 21. 8 times 3. 8 times 3, 24. So you can see here that we had 7 eighths, 7 eighths, and we multiplied it by 3. 1, 2, 3, and this was our new equivalent fraction, 21 over 24. Let's see what happens with this other one. 1 times 8, 8. 3 times 8, I don't know, 24. We could do 3 times 8, and that's what we actually did, 24 right there. But we already knew that. That's why we were multiplying by 3. Now when we add these up, all we have to do is add the numerator, keep the denominator. We wanted to have common parts, which is 24. So now we have circle, imagine, divided into 24 pieces. We know that we have 21 of the pieces highlighted in one of them and 8 in the other. Now, how many pieces would you have all together if you combine 21 and 8? You'd have 29 over 24. So out of a piece that can hold 24, you have 29 of them, which means you have extra. Whenever we were going through the process, we talked about this. What's it called when the numerator or the top number is larger? It's called you almost had it, it's an improper fraction. So the question I'd ask you following this is, okay, cool. How many times does 24 fit into 29? You got it right 100% of the time. And we would say 1. It goes in one time. And then I'd say, well, what's left over? Because if we're talking about a circle with 24 pieces and you have 29 pieces, that means you have some just laying outside of the circle. So how many? Well, 24 is 25, 26, 27, 28, 29. 5 away out of the 24. So that means you had an excess of 5. This is also called a remainder of 5. You filled up a circle of 24 and you had 5 left over just sitting around. Now if you pulled over another 24, you had 5 of them filled in. You have 1 whole one and 5 of 24 of another. So this can't be reduced, and one way we can check this is, what goes into 5? 1 and 5. 1 goes into 24, but it's not going to make it any smaller. Does 5 go into 24? No, it does not. We can check that by going over to 5 and seeing if 24 appears anywhere in the multiplication chart. The answer is no, it does not. So I want to just highlight, not literally, because I've been doing plenty of that, but I want to highlight how similar subtraction is to addition in that it's the exact same. I'm going to replicate this problem, 7 eighths and 1/3, as subtraction. So there I am, the highlighter. 7 eighths minus 1/3. Our first step was always to count by the denominator because we can see that they're different. That's a problem. That means we can't do this problem yet. So 8 and 3, I'm still doing the same thing. 3, 6, not 19. I almost put 19 again. 12, 15, 18, 21, 24. And again, we could always go back and take a look at what is it that we're looking for. 24, got it, okay. So then we're counting, all right, so I see a 24 and then 8. Oh, there's a 24. Okay, got it. Got it. That's what I'm looking for. Yes, got it. So let's take a look. 7/8. How did we get there? All right, so here's 7/8. We got, all right, so 21 over 24. So 21 over 24 minus, let's go back to that 1/3 and see how we got to 24. 1 over 3, okay, so 1 over 3, 8 over 24. Cool, there's the new fraction that we have for there. Look at that. That's what we had for the addition one too. 8 over 24. You could always do the same thing we did in the last problem. Go, how many times I multiply by 8? 1, 2, 3, so times 3. There we do the bottom, do the top. 1, 2, 3, 4, 5, 6, 7, 8. Then multiply by 8. But you do the bottom, do the top. Take a guess what 7 times 3 is. 21. Take a guess what 8 times 24. Take a guess what 8. Take it. 24. So the same thing happens with this is you have the denominator. Sweet. Those are the same number. We created equivalent fractions. All right. We started with 7/8. Now we have 21 over 24. We started with 1/3. Now we have 8 over 24. All you got to do is just subtract the top numbers. 21 minus 8. Oh gosh, I don't know. 21 minus 8. 2, 3, 13. Okay, whew. 13 over 24. 13 is prime, and I know that if I count by 13s that it's not going to be 26, so there is your final answer. This is the process you go through every single time.